All right, hello and welcome. I'm going to be picking up and continuing off of a conversation I was having with Zachy on my buddy Boke's Discord, and he had some flat Earth questions for me. And I told him I would make him a video response, to provide some demonstrations and context on to answer his question. So let's get to his question. So he says here, I have a theory about how to debunk either flat Earth or spherical Earth depending on the conclusion. It goes like this. In a flat Earth model, the sun and moon are close to us, and the sun is not bright and powerful enough to light up the entire flat Earth beneath us. Therefore, the light would not be able to reach and affect the other planets, and how we view their reflections from Earth, like we do with the moon. I would I would conclude that the Earth is a sphere and the sun is far away if the other planets' reflections is affected by their location compared to the sun's location. Do you know whether this is the case? And then he followed up and said, let's see here. How is it possible to see the reflections of other planets? I mean, what are the sources of their light and reflections, if not the sun, since their light is, since the light is only reserved for Earth? And to give some context to why he's talking about that, just for whoever else may be watching this video, I recommended him this video. Terry, it's really simple. Terry. Okay, this one right here.
Here's what we want to.
Okay. All right. So I was showing him the close sun right here. So he's thinking that, the close sun is not going to be able to light up and reflect off the planets. So this is and I was kind of explaining to him that this is that the reason that this isn't really even an analogous comparison is that it's kind of conflating the two models, right? So in the heliocentric model, the planets are rocks and balls of gas, and they're not, they're not their own sources of light. So they're dependent on the reflection of the sun and the brightness of the sun and all that, which is good for us because it makes it makes the brightness and stuff of the sun subjected to the inverse square law and things like that. So we can we can kind of analyze the story of heliocentric mythology and see if these distances and sizes and brightnesses all correspond to a definitive proof of the heliocentric model, or if the distances could be much closer, and would we even really know the difference in terms of the math they use? And the answer is no. So we'll kind of get into the situation here and explain. So my answer, of course, to this question about the planet's light sources is that they are the planets are wandering stars, and that they are their own light sources. The images and everything that were given from NASA and mainstream, astronomy, where they take images, stack them, process them, and superimpose other images on top of them to add clarity, and they touch them up with Photoshop and all these things, and we get these nice beautiful pictures, and we think that this is like a representation of what we see in the sky. So we're gonna get into all of that and learn some new concepts, go over some concepts, and apply everything at the end, and see if we can decipher if what heliocentrism says about the lights in the sky, if it matches reality or not. So without further ado, I hope you enjoy, and we'll get right into it. So first, we're going to start with the attenuation of light. Um, light doesn't travel, forever at the same intensity. So even in the space-time paradigms, right, they say that there's these sections of, large sections of gas and dust and all these things. All of that stuff would affect the light distribution and how we see it, and from the distances that they say. So just keep that in mind. So we have a sun that's 93 million miles away from Earth as a baseline, and as we continue on, we'll learn some additional concepts. So the big one here that's really relevant to the situation is the inverse square law. So I'll read a little bit of this and then we'll watch a couple of demonstrations to see how this applies, and then we'll start applying it to the sky. So the inverse square law. S represents the light source, while R represents the measured points. The lines represent the flux emanating from the source and the fluxes. The total number of flux lines depends on the strength of the source, and it's constant and increasing, and is constant with increasing distance, where the greater density of the flux lines per unit area, means a stronger energy field. The density of the flux lines is inversely proportional to the square of the distance of the source, because the surface area of a sphere increases with the square of the radius. Thus, the field intensity is inversely proportional to the square of the distance of the source. So it sounds like a lot, but what it basically means is that as you double the distance away from the source, the intensity drops off by a fourth. It's pretty straightforward. And for something like radar, right? So when we're talking in terms of reflections, right? So they say that, these planets and all these things, we see them via reflections, right? So think about that. Right here it says radar energy expands both signals during transmission and the reflected return. So the inverse square for both paths means that radar receives energy according to the inverse fourth power of the range. So basically, instead of, what they're saying here is that they 4 times the amount of power that they put into radar signals, because the radar has to bounce back and travel. So this intensity, as the radar signal is dropping off over distance, this has to be compensated for before they even send the signal out, so that they can so that they know how far they can send the signal and get an accurate reading back, because this is going to keep dropping off, right? So it's going to be to travel there, or to travel a distance and back, it's going to 4x the drop off rate, right? So that's basically what they're saying there. So just some more interesting factoids about the inverse square law and how that applies to propagation of basically everything, especially when you're talking about light and electromagnetic radiation and all that. So here's a quick example. We're going to watch this video. We're going to watch a couple of videos actually, and I'll just kind of chime in. Oh shoot, let me change to full screen mode. So we'll watch a couple of videos here, and I'll just chime in as necessary. Yeah, here we go. So this is a practical demonstration of the inverse square law on a small scale. We'll watch these videos at 2x speed. I'll have links in the description, so you can go back and watch them at 1x speed if there's a point that's unclear, or you want to get further context on something, or you feel like you missed something. So here we go. Just go ahead and play this out.
The square law, but show you really quickly and practically what it is, what it does, and how you can use it. Hello Yasmin, thank you for joining us. We're actually just taking a minute out. We're filming a brand new course on single light portraiture. It's going great, but I thought this might be a nice little unit to break out and show you guys. It can be complicated, but it can be really simple. So throughout this, we're going to be staying a socially distanced 6 feet apart, but that's good to give a little bit of reference. So reach your arm out. You can almost touch the flash there, ish. Yes. Remember about that distance. We're going to demonstrate how the light falls off by keeping the light the same distance from her. So the theory goes, or the formula is, which you don't need to memorize, is essentially that as light travels from its source, it spreads, and as it spreads, it drops off in intensity. So the light coming right out of here is at maximum intensity. If I'm just 5 inches away from that, it's going to have loads and loads of power hitting my hand. But once my hand is back here, we're getting a lot less light per square inch on my hand. It's spread out more, and it's dropped off in power per square inch. The exact number is that as you double the distance, the amount of light power drops off by 2 stops. So you double the distance, and you halve, and then halve again the power. So double the distance, and you get a quarter of the power. So if, let's say, just making up the numbers, she is 3 foot from the light right now, and I've set up all of my settings so she's correctly lit. If I now move it to 6 foot away, she'll only be getting a quarter of the amount of light from my flash, and she's going to be really underexposed. But that has a nice little side benefit. If we want to keep a white wall white, or turn it to any shade of gray, or bring it to black, we can do that by limiting the amount of light that reaches the wall. So I'll tell you it first in theory, and then second we'll demonstrate it. Can you just walk back and lean right against the wall? So here, if we have the light still, basically 3 foot from her, I set up my settings, she's correctly exposed, the light will hit her, expose her, and then it only has an inch or 2 to hit the wall. So the light won't fall off in intensity much in that last inch or 2. Makes pretty good sense, right? We're talking 3 foot distance to 3.2 foot distance. Now, if you come out with me to about here, stop. So let's say now she is 3 foot away, but the wall is 6 foot away. 3 foot to her, my settings are still the same, so we're still getting enough light to light her. But then from her to the wall, it's another 3 foot. So that's double the distance. So what is hitting her is X, what's hitting the wall is a quarter of X. It's 2 stops less intense. So there we're going to see our white wall start to turn gray. Then if you walk forward to the start of the rug, then here we've got the light 3 foot away, and then the wall is 9 foot away. So as we double the distance, 3 to 6, we're losing 2 stops, another 3 foot, maybe another stop or so. And if we come even further and make it 3 foot to her and 12 foot to the wall, we're going to find that the light falls off immensely and the background goes close to black. So we can, without doing anything else, not changing the flash power, not changing any of our camera settings, we can use that ratio to our benefit. So now let's actually do it. Let's go back to the wall. From the window to the wall. So how's that distance for you?
Oh, my dude said to the windows to the wall. All right, that's my mandatory commentary for the 4-minute mark of the video to avoid a copyright strike. That's my commentary so far. But yeah, so basically you kind of get the concept there. The source and how far away the observer is from the source, you're going to get a directly inverse proportional relationship to how bright you're going to see that source emitting light to you, right? And then we'll see he's going to take some pictures and kind of, or not kind of, he's going to take some pictures and demonstrate what that intensity fall off looks like on just the small scale. So we'll continue on here and get this one out of the way. We're almost done.
Okay, so go right to the wall, like lean against the wall. Okay, just bring up the height a little. So FYI, although you can't just transpose these settings to your own situation, I am at ISO 100, f8 and 1/160th of a second with no flash. Here's how our scene looks. Nothing really there. Popping in the flash, and I currently have the Nissan DI700 on half power going through this little softbox. I'll pop all the links below. So let's go just in on head and shoulders. Okay, pretty good exposure. And you can see we're getting a clear shadow on the wall there from her because of the direction of light. But where there is light hitting the wall, it's nice and bright. So let's get a wide shot on the same scene just to show you. So you can see the vignette. That's how far the softbox is extending in the scene. So let's bring you out just 2 big steps. Yep, perfect. Is that about the same distance to you? So you can do this all precisely. Her arm isn't changing in length, so it's close enough. Okay. So now, you see the background? So comparing the first and second there, you can see the background's already getting darker. The grays are getting darker. So let's come forward to the edge of the rug now. Okay. Let me know, is that about the same distance? Okay, great. Same shot. Are we doing serious smiles or scary? What are we doing today? I can never tell with you. Oh, good a laugh. I'll take a laugh. Okay, so that's starting to get darker in the background. Show you the full scene here. Reminding you that what I said, as the light travels from the flash, it spreads, and as it spreads, it drops off in intensity. The analogy I like to use is, let's imagine that this flash power that I have said is a bucket of paint, okay? So if I want to paint the wall with that paint or that light, then I can either paint a really small area really thickly, or I can do a really thin coat over the entire wall. As it spreads, it has to become less thick or less intense. So let's come another 3 foot or so forward. And is that about right? Take a step forward until it's in the right spot. Okay, so now we're going to see the background is really getting dark. Nice, nice, nice. So you can see what we're working with here. Let's just get a wide one as I tuck myself into the corner of the room. We can actually do that. Let me go as far back as I possibly can. And you walk into that. I'm breaking the door. Okay, so this is as much as I can do in this room without readjusting all the settings. So on those, you can see we are pretty much getting the background close to black. Not total black, but close. So it's pretty straightforward, folks. Get the light close to your subject and far from the background, and you'll make the background much darker than your subject. Put the subject.
All right, I think we pretty much got the point there on that one. So thanks for that video, Matt Granger. Very nice. Actually, let me save this link for the description. Okay, continue on. Okay, so this is scale. This is scale invariance. So this is how angular resolution and angular size has been used to derive these distances for how far away we see things. And what you're gonna see is that the system of like 93 million miles and the moon's this far away at 250,000 miles or something, 230,000. You're going to see how all this works and how these distances don't matter at all, and what the scaling system is for this. So go ahead.
I was
start
taught
this.
that the sun is 93.
Oh, yeah, I'm sorry. This. One second. All right, this video is from Jaronism. This is from a mirror channel that backed this up. So thank you, whoever this guy is that runs this mirror channel. It's a great video for demonstrating scale invariance and the math used to, give us these distances and derive everything, right? So here we go.
Million miles away. How about you? What were you taught? My guess is the same. Were you taught how we know it? Well, possibly your answer would be trigonometry. A hero of all Earth believers everywhere states this is the way that we know. You can verify the distance of the sun.
Correct.
Based off what?
Trigonometry.
So using trigonometry, we can then figure out the distance to the sun. But the sun and the moon appear to be the same size in the sky. So if we use trigonometry, then I guess the moon is also 93 million miles away? Is that what you were taught? Me neither. So I'm confused. I thought that math could be used to give us these facts. Does math tell us what reality is? Because the same religious zealot hero has also repeatedly cried,
Math is reality.
were you taught this? Well, if it is reality, then the sun is 93 million miles and can't be, say, I don't know, 229 million miles. Both can't be true, right? Both are certainly not reality. So So obviously, if
Math is reality.
then math must be able to tell us which is right, 93 million or 229 million. Well, then it's time to prove our reality. Let's see what the math says. Thanks for joining me. This is Jaren's.
Guidance is internal. Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
You can tell it's real because it looks so fake. 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 Because it looks so fake.
What's going on, everyone? It's Jaren from Jarenism, back with another video for you today. How true is the model of the solar system that we have? Well, ask any astronomer or
Howdy,
fanboy NASA or liar like Steve McRae, and you'll get told it is 100% fact. It is as true can be. Well, I shall disprove this at once and show how a presupposition, dogmatic faith, can make their religious beliefs seem true when they are anything but that. So, we've been told that the sun is 93 million miles away. How do we know this? Well, let's begin with some facts. What do we know about the sun? Well, it emits light. What else? Well, the rest is a lot like the idea of Santa delivering gifts to every child on Christmas Eve. Even little children think it sounds crazy, but because authority figures are the ones telling them the story and they don't know any better, and while cookies are eaten in the morning, it becomes believable to most children. So much the same, the ideas of the distance to the sun come with the same nuggets. You and I might not know any better, so we look to the authorities for the truth. So we are told that it's 93 million miles, and with that comes some eating cookies in the morning. They have filled our knowledge gap with their own cleverly constructed explanations of what we see, and then all we can see is what looks like beautifully wrapped presents, and then we find some cookie crumbs as evidence of their fictional Santa Claus. One way they do this is with the idea of angular size. So, back to our facts. The sun emits light. Anything else that we know about the sun? Sure, we know its angular size or its apparent diameter. This is the apparent size or angular diameter of a sky item. How large something appears in our eye or telescope. The sun and moon both appear to be about 31 or 32 arc minutes, or that's equal to 1/2 degree. So I want to point out something that I certainly wasn't taught in school, and it's no wonder why. Scaling invariance. Feel free to look it up on Wikipedia, and you'll see that in physics, mathematics, statistics, and economics, scale invariance is a feature of objects or laws that do not change if scales of length, energy, or other variables are multiplied by a common factor. As long as all of your inputs are scaled correctly, the entire body is indifferent. It doesn't vary. One of those things, the entire solar system model. But wait, the mathematics of the solar system is facts. Indisputable fact, right? Well, not when the entire models are based off of angular size, because angular size tells us what size something is in our eye, not its true distance or its true size. We need more info. So hold up here. I thought
Math is reality.
it has to be. 2 plus 2 equals 4. That's reality. 30 plus 15 equals 45. Period. Well, is that true? A man has 30 cars, and he added 15 cars. He now has 45 cars. Is this true? Well, if there was such a man, and he did add said cars to his 30-car collection, then the statement is true. Is it reality? Well, I'd have to first prove said man exists, as do his 30 cars, as do the 15 he added. That makes it reality. So is math reality? Well, only when all elements of the equation are proven true is math reality. Is 30 plus 15 45? Yes, true. Or is it? What if it was 30 plus 15 half cars? Oh, that's different. We need to prove and know what each number refers to. If I have $3 million and I add $1 million, does that mean I have $4 million? Well, if I had $3 million in reality and added $1 million in reality, then I'd have $4 million. But to claim it is reality, I must first prove that I have what I claim. So if the entire model of the solar system is based off of angular size, who has proven the actual distance and sizes of said items? Is the solar system reality, or is it a cartoon? I mean, is the solar system a fact, or is it fiction? This clearly has to be solved already, correct? What if I told you it wasn't? What if it was all just numbers? What if it was all just math, and they wanted you to believe that math was reality, but they forgot about the other part? They have to prove all the elements of the math. Let me explain. So the angular size of the sun and moon is approximately 31 or 32 arc minutes, which equals 0.53 degrees. Now, that does work for a sun 93 million miles away and 864,337 miles wide. But it also works for a sun 229 million miles away and 2 million miles wide. Wait, what are you saying? The sun would look way bigger in the sky. No, it wouldn't. It would look the same as if it was 93 million, or if it was 46,701,000 miles away and 432,000 miles wide. The distances and sizes can be scaled indifferently. Our observations from Earth would be identical. If the sun was 23,351,000 miles away and 216,000 miles wide, it would be the same as if it were 11,675,000 miles away and 108,000 miles wide. Identical to the sun that's 6,053,900 miles distant and 56,000 miles in diameter, which is no different than a sun 3,026,900 miles away and 28,000 miles wide, which is just the same as a sun 1.5 million miles away and 14,000 miles wide. Okay, hold up. What about our orbit around the sun? Well, sure. You know the distance, which is the radius of our orbit. 2 pi r gives us 9,504,780 miles as our yearly orbit. Divide that by 365 and that by 24, and you get 1,085 miles per hour as our new speed instead of 66,000 miles per hour. And our observations change none. And since you feel no spin or travel at all, well, then nothing changes at all. Man, math is so reality. Whether the sun is 756,730 miles away and 7,000 miles wide, or even, heaven forbid, 3,500 miles away and 32 miles in diameter, it makes no difference. You liar. What about eclipses? Well, as I said earlier, we can't just change the sun. We have to scale the moon too. So yes, as long as you divide or multiply by the same number, you'll be fine. So yes, the moon is 0.53 degrees as well, which works out to being 233,400 miles away and 2,159 miles in diameter, as it is about 400 times as small and 400 times as close as the sun. But it would work the same if the sun was 100 times as big and 100 times as far, so that the moon was actually 58,376 miles away and 540 miles wide. Well, then an eclipse would happen because the sun is 100 times as far, so 6,053,900 miles away and 56,000 miles wide. Or the moon could be 14,594 miles away and 135 miles wide, or 864 miles away and 8 miles wide, or even, heaven forbid, 3,567 miles away and 33 miles wide. It could be half that size, 1,729 miles away and 16 miles wide, and then the sun could be double at 3,567 miles and 32 miles wide. Same observation from Earth, of course, because math is reality. Now, some things could help us determine.
All right, so just to cut in real quick here. Do you see the pattern here? Like none of these numbers matter once you have the initial system set up. If you're basing it all entirely off of angular size, just how big something appears in the sky, and because the sun and the moon are the same size, if you just adjust those proportionally, it doesn't. Nothing changes, right? So there's no way to verify any of these distances that they tell us or that they give us, and this entire system scales with invariance, right? So they change one thing, the whole thing changes uniformly.
Which distance was more likely to be correct? For example, the inverse square law of light that says that given a certain brightness or intensity, it is inversely proportional to the square of the distance. So if we know how bright the moon is, each time we half our distance, the brightness increases by 4 times. So you see, we can say the moon is 100 lumens, and it doesn't really matter which number we put.
All right. I'm going to, for this part, I'm going to slow it down when it's getting into how this also applies to the inverse square law, because the next couple of videos is going to be about the inverse square law in regards to the brightness of the moon in the Apollo missions. If we're going to take heliocentrism on its word, we can actually figure out how bright the surface of the moon would be based on the inverse square law by just reverse engineering it. So I'm going to slow this part down and we'll continue on, but it's basically the same concept moving forward with the inverse square law as we learned earlier about having the distance and you lose a fourth of the brightness. Well, you can reverse engineer that backwards where you gain the brightness at half the distance. So we'll see how that all works out, and then we'll see a practical demonstration of that as well.
Place on there as the result will be the same. So at 240,000 miles, we have 100 lumens. At 120,000 miles, we have 400 lumens. At 60,000, we have 1,600 lumens. At 30,000, we have 6,400 lumens, and so on and so forth, and so on and so forth, till we get down to 1,000 miles distance. When we're 1,000 miles away from the moon, the lumen should be 6,553,000. So if we divide that by the original 100,
This should...
we see that from 1,000 miles away, the moon would be 65,530 times brighter than it is from Earth.
So keep this in mind when reversing the inverse square law. And what they'll say, a common rebuttal to the inverse square laws, they'll say, you can't inverse square law reflections. Well, clearly you can, So anyway, just let this continue out here. So as bright as we see, hang on, I'll let him explain it again so that it's clear. Basically, as bright as we see the moon, on a full moon on Earth, right? So if you took that as 1 lumen or even 0.1 lumen, it still gets ridiculous when you reverse engineer it back with the inverse square law. By the time you get to like 1,000 miles away from the moon, you're at 6,053,000 or 500,000 lumens. It's insane.
Is that what we saw? Well, here's some photos from Apollo 17 from 800 miles from the moon. And you tell me, is that moon 65,530 times as bright as it is from Earth? Of course not. So one thing or the other isn't true. Either we've never been to the moon or the moon is far closer. What can't be true is the moon is the distance that they tell us and that man has been there. Another way that we can determine if the distances we are given are correct is to imagine the sun, I don't know, say it's 1,000 miles away. The sun would take up the entire day sky, correct? Okay, so let's make it now 93 million miles away. Okay, now if you hold a dime out at arm's length, that's about the size of the sun at 93 million miles or 8 light minutes. So now double that distance. Well, that's now a light 16 minutes. Okay, double it again. Well, now we're at a light half hour. Okay, double that again, and we're now at a light hour, and I doubt you'd be able to see the sun. But let's multiply that by 24, and now, finally, we're at a light day. No chance you would see the sun. But now we still have to multiply that by 365 times more to get to a light year. Think about that, people. How would we see any star, considering no star is that close? Nonsense, mathematical reality. I mean, really, to think that we could see 25 trillion miles, remember that a trillion seconds is 31,000 years. Think about that and realize that the closest star, other than the sun, is 25 trillion miles. Yole. Now, wait a minute, you yell. Wouldn't the planets have to change as well? Well, of course. Their orbits, sizes, and distance would all be scaled appropriately. Here's an easy way to see it in action. Take these numbers 0, 3, 6, and start doubling. 12, 24, 56, 108. Okay, now add 4 to each. So 0 becomes 4, 3 becomes 7, 6 becomes 10, 12 becomes 16, 24 becomes 28, 56 becomes 60, and 108 becomes 112. Now divide by 10. So 4 becomes 0.4, 7 becomes 0.7, 10 becomes 1.0, 16 becomes 1.6, 28 becomes 2.8, 60 becomes 6.0, and 111 or 112 becomes 11.2. Now, does that look familiar? Well, it should. 0.4 is Mercury's AU, 0.7 is Venus, 1.0 is Earth, 1.6 is Mars, 2.8 is Ceres, 6.0 is Jupiter, and 11.2 is Saturn. Now, of course, those are approximate numbers as they change based on their distance from the sun, which is changing all the time. So now you have the distances from the sun, 93 million miles times the AU. So Mercury is 37.2 million, Venus is 65.1 million, Earth is 93 million, Mars is 148.8 million, Jupiter is 558 million, and Saturn's about a billion. Of course, you can then figure out exactly what their distance from Earth is, with Mercury being 56 million, Venus being 26 million, Mars being 34 million, and Jupiter being 367 million miles from Earth. But what if 1 AU is actually 3,567 miles, not 93 million? Well, 3,567 is to 93 million as 1 is to 26,072. So scale it all by 1 26,072nd, or I'm not really sure. Then you can even figure out the distance from the Earth. So Mercury is 2,147 miles, Venus is 997, Mars is 1,304, all miles from Earth. Now wait, wouldn't they need to be smaller? And, well, of course, scaling invariance. So Mercury is actually 2,147 miles away, and with its angular size, it would come out to 0.11 miles, so that would be 603 feet in diameter. And Venus at 997 miles from Earth would have a 0.28 mile diameter, or 1,520 feet. And Jupiter would be 14,076 miles away and 3.40 miles wide. And we can check our work as well, because 3.4 miles is 1/10 of the sun size at 33 miles in diameter, which matches the current model with Jupiter 84,000 miles wide and the sun 860,000 miles wide. No, you cry. Give me my Santa back. Wouldn't gravity be different? Well, would it? Well, here's the thing. Whatever amount of gravity has been given to the Earth or the sun or any of the other planets is based off mass. Well, we can easily just change the mass of the sun. Who is weighing it? The answer is no one. And we can change the mass of the Earth. Who is weighing it? Cavendish in his shed? Give me a break. And quit it with your religious stories. It's becoming silly. But clearly, the silliest thing ever said is
math is reality,
which is the biggest load of bull ever stated as fact. I mean, really. If you ever hear that clown trying to assert that again, tell him you don't care about his religious precepts.
All right, so that's the scale invariance of the heliocentric model. None of the distances or anything like that matter. It's all been derived so that they can basically put the sun super far away, so that when they do what is it, like sticks and shadows at the equinoxes and all that, they can claim that they're, you know, on a ball looking off at an angle. But that doesn't really work either with an azimuthal grid, which is kind of a separate subject. But anyway, I digress. The main moral of the story here is that with scaling invariance and basing it off of just angular size of how something appears in the sky, there's without a way to verify the actual measurement of how big they're saying it is. You know, you could derive an entire system based off of that, and it wouldn't have to be true at all. Everything that we see would be the exact same. Is the real takeaway from that. So as Jaron was saying, with the inverse square law and light minutes, and how far or how big the sun would appear at arm's length, you know, based on its distance, right? So at 93 million miles, the sun, that's 860,000 miles wide, right? At arm's length on Earth, it's about the size of a dime, right? So here's what the perspective looks like on Earth. Then if you increase that distance, it gets a little smaller. So, you know, whatever's smaller than a dime, a penny or whatever, I'm not sure on the sizes. Anyway, you get to Jupiter, even smaller, Saturn, Neptune, Uranus, or Uranus, Neptune. So Neptune is 2.75 billion miles away from Earth in the heliocentric model. And assuming C is true at 186,282 miles per second, that's 4 light hours away. So if you remember back to the video when Jaron was saying, you know, at one light day, you know, would you even still be able to see the sun? And, you know, if everything were true about how they describe space and the heliocentric model and stuff, absolutely not. You wouldn't be able to see any of the stars or anything like that. Now, the reason that they claim that we can see these things at these distances is that they're all super, like, they say the sun's 860,000 miles wide, right? Now, the other stars, they say are like hundreds and thousands of times bigger. How much larger are the other stars compared to the sun? Let me see if I can find you a quick comparison thing, there's usually a couple of these. You can see the other stars. Okay, right here. Perfect. This works. So we got big is the sun. Where's the... There's usually like tons of cartoon graphics of this, but when I wanted to find one, obviously it can't be done, right? These are all solar system. Where's the other stars? Anyway, they say that the other ones are just, astronomically huge. You can't even fathom it, right? And that because of this size relationship and the way that light travels, infinitely, and the inverse square law doesn't actually go to zero, it tends to zero infinitely. That we just see these like finite dot points in the sky, and that's how it works. But in reality, the angular size would drop off. The intensity of light would drop off. You could see it happening here on the small scale within our local solar system, just at Neptune at 4 light hours away. So if you keep increasing that to a light day, get out of here, dude. And then a light year. It's ridiculous. So we'll go ahead and continue on here. So here was the size of Neptune that I pulled up earlier to look up that. Now we're going to watch this video about the inverse square law in the moon to kind of see how that applies. So Jaron was kind of touching on that in the video, but now we're going to see a practical demonstration of it as well.
How bright would the moon be if you were standing on it? So I'm going to light up a piece of paper with the moon and take a look. So I couldn't find any paper, so I wrote my name on a piece of paper towel. And as you can see, with the moonlight, I can read my name perfectly fine. Now let's compare it to a regular light. Okay, here's a big building. Let's make it dark in here. Okay, I mounted a 60-watt light bulb to the wall. I use a 60 watter because everybody knows how bright a 60-watt light bulb is. And about 50 feet away, here's what the sheet of paper looks like. Okay, so the moon one is on the right, and the regular light bulb is on the left. So you can see they're pretty similar. Now, don't get your panties in a bunch. I know you should be using a light meter and all that stuff. Wait till the end. It's not going to matter. Okay, so the moon is 1,256,640,000 feet from the Earth. Now, a 60-watt light bulb at 50 feet is roughly the same brightness as a full moon. You can read the paper about the same. So we're going to use the inverse square law. Okay, so we're going to take 50 times 25 million, and that puts us at 1,250,000, which is pretty close. Now we're going to square this number. So 25 million squared is 625 trillion. So now we got to take 625 trillion and times it by 60 watts, and we get 3.7 gajillion, bazillion, zillion plus 16. Like, this number is so big that I think my calculator exploded. So you can see there's a huge problem here, right? So let's just call it 1 to 1, okay? Let's just go 1 to 1 ratio. Instead of like 1 to 5 bazillion, gajillion, bazillion, jillion, we're just going to go 1 to 1. And let's see what it looks like. Okay, here's our little moon landing guy. Okay, let's land him on the moon at 1 to 1, 60 watts. Does that look normal to you? Is that what the moon landing looked like? Come on.
The inverse square law of light is simply not applicable to anything in space. Flat earthers discovered that the moonlight on the moon's surface would be intensely blinding based on the official numbers of the heliocentric model. The inverse square law of light works like this. If you place a 100 lumen bulb in a floodlight that shines on only 1 square meter of surface, that surface will be lit at 100 lux. However, if you back the floodlight away to shine on 4 square meters, the surface is now lit with 25 lux. The intensity of light is inversely proportional to the square of the distance. This means that as the distance from a light source increases, the intensity of light is equal to a value multiplied by 1 over d squared. The full moon, which is supposed to be reflecting sunlight, has an illuminance up to 1 lux on the Earth's surface. Look at this diagram and imagine that the light source is the moon and you're standing on the Earth's surface there on the bottom right corner. Each step higher you go, the moonlight gets more intense. So, based on the official distance to the moon and a 1 lux strength of moonlight on the Earth's surface, the Apollo astronauts would have experienced many thousands of times more luminance on the moon's surface than direct sunlight on Earth. Every photo of the moon's surface would have been impossible and washed out.
Not only would it have been impossible and washed out, at that brightness, they would have been vaporized. Like that, you couldn't even land on the moon. It's crazy. So thanks, Ben, for that video on the inverse square law, and it was the guy that did the original calculations, Anthony Bear. Thank you for those videos. So I'm not going to play this video out, but I'll link it in the description. This is stellar parallax, and this is how they derive the distances for the stars that are really far away. It's complete nonsense based on the assumption that the Earth is moving. And if the Earth isn't moving and the sky is moving above us, if you just assume the distance of 93 million miles anyway and double it 6 months, or for an observation 6 months later, you can get the baseline of a triangle, even though the Earth hasn't moved at all, and you could still get all these calculations to these distances under the same methods, and everything would, work out as if you were calculating distances of, trillions and billions and zillions of miles away. This is a really good and concise video on that, but I'm not gonna play it to just to keep this moving along here, as we're almost done. Let's see. So we'll wrap up here. Actually, I'm not gonna play it on my own video again. So we'll wrap up here on what the planets, so-called planets, look like through actual telescopes, without the superimposing and stacking of images and all these things. So here we go. That audio is killing me, so sorry about that. All right, so we got Jupiter here. This is what people see when they look at it for real with their own optics, right? So when you stack and process it, you get a little more clarity and definition. But keep in mind, in heliocentric mythology, this is being reflected from the sun. These are different. What is it? Different gases and all these things, different bands, but it's all reflecting back, uniformly enough to give us that. Crazy. So we'll just wrap this one up here. So that was Jupiter and Saturn. We'll look at a couple of other ones on the outro here. These songs. Play this faster here. Alright, so here we go. Saturn. The magnitude is the brightness, and it doesn't have a wind speed, so, So there's Uranus, right? So they're saying that these are physical objects reflecting light, right? And this is Neptune, so at 2.75 billion miles away, aka 4 light minutes. And this is what we're seeing like in reality here, right? So I hope that adds some clarity on the two models here. And that's why it's important to realize that we're looking at two separate, explanations here, right? So when trying to analyze, the flat Earth model and the heliocentric model, it's really important to just kind of separate the information that we've been given, for the heliocentric model, and just look at it from a different paradigm. So the explanation being that the luminaries are their own sources of light, I think makes way more sense than the light with the distances and sizes that they show us here. So, all right, I hope you enjoyed the video, and if you have any further questions, don't hesitate to ask. I'm happy to answer anything you got. All right, thanks. You have a good day.